All right, let's jump right in. Today, we're decoding a document that's absolutely core to engineering, but let's be honest, can look like a secret language. We're talking about the P&ID for a centrifugal compressor. We are going to translate this blueprint and show you exactly how to read it like a pro.
Yeah, you look at something like this for the first time, and it's easy to just see a chaotic mess of lines and symbols, right? A piping and instrumentation diagram, or P&ID, can feel pretty overwhelming. You're probably thinking, where do I even start? But here's the thing, it's not a mess at all. This is actually an incredibly organized, strategic blueprint. Think of it as a universal language that lets engineers from anywhere in the world, in any discipline, look at this and know exactly how the system is supposed to work.
And here's my promise to you. By the end of this, you won't see a mess of lines anymore. You'll see a story. The story of a gas's journey through this whole system. So, let's get into it.
To make sense of all this, we're going to approach this P&ID just like a map. We're going to follow the path of the gas as it moves through the entire compressor loop from the very beginning to the very end.
Now, that journey really has three main routes that you have to know. First, you've got the suction path. That's the entrance. Second, the discharge path. That's the exit, where all the high-pressure gas leaves. And third, and this one's super important, the recycle path. This is the system's main safety route. Okay, let's start at the beginning. As gas flows into the system, it enters what we call the suction path. This is the low-pressure side of our map.
And the first major piece of equipment it runs into is the suction scrubber. The best way to think about this thing is as the compressor's personal bodyguard. Its entire job is to knock out any little droplets of liquid from the gas. Why? Because you absolutely cannot compress a liquid. If liquid gets into that fast-spinning compressor, the damage is catastrophic. For a compressor, liquids are the killers, period.
All right, so after the gas gets squeezed and its pressure is massively cranked up, it shoots into the discharge path. This is the high-pressure side of our system, and it has its own really important safety gear. Right after the compressor, you are always going to find this symbol for a check valve. This piece of hardware is brilliantly simple, but it's absolutely vital. It's just a one-way door. It lets all that high-pressure gas flow out, but if the system ever shuts down, it slams shut instantly. It stops that high-pressure gas from rushing backwards and trying to spin the compressor in reverse, which would totally wreck it.
Okay, so we've covered the entrance and the exit. But for any control engineer, the most important path on this whole diagram is the one that connects the exit right back to the entrance. And that's the recycle line.
And the star of this recycle line is the anti-surge valve, or ASV. This is the system's most critical safety control. See, under certain conditions, the flow inside a compressor can get unstable and violently reverse. It's a dangerous event called surge. To stop that from ever happening, the ASV can pop open in a split second, creating a bypass that sends gas from the outlet right back to the inlet. It keeps everything stable and the machine safe.
So we can follow the flow of gas now, right? We know the main roads on the map. But what about all those circles and letters all over the place? To really read the map, we need to understand the grammar of this language.
And that grammar is all laid out in a global standard called ISA 5.1. This is the rulebook. It's what tells us that PT in a circle stands for a pressure transmitter or that TT is a temperature transmitter. It's the reason an engineer anywhere in the world can understand this drawing.
Okay, this next part is pretty cool. Now that we know the path and the symbols, let's look closer at the pipes themselves. Because a P&ID isn't just a schematic. It's a direct reflection of the laws of physics.
So have you ever noticed this detail? On pretty much any compressor P&ID, the suction pipe coming in is always wider than the discharge pipe going out. That is not an accident. There's a really simple and kind of elegant physics reason for it. And that reason comes down to this fundamental formula. Q equals A times V. All this means is that the flow rate of the gas, Q, is equal to the cross-sectional area of the pipe, how fat it is, multiplied by the velocity of the gas moving through it. And this table just shows you exactly how it works. On the suction side, you've got low pressure, so the gas takes up a really big volume. To move that big volume without the gas velocity getting crazy high, you need a big pipe area. Simple. But then, on the discharge side, the gas is super compressed. It takes up way less volume. So you can use a smaller pipe area and keep the velocity in a safe range. It's just simple physics, made visible right there on the diagram.
So we can see how physics shapes the blueprint, but how does that 2D document actually turn into a 3D reality? Well, the P&ID is the foundation for a really sophisticated design process that takes the plan from a computer screen into a real-world industrial plant.
The whole thing starts with design software, where engineers actually draw the P&ID. Then they use 3D visualization tools to basically walk through a virtual model of the plant, making sure everything fits. And that all leads to installing the actual hardware in the field, like this suction strainer, which, by the way, everybody calls a witch hat for obvious reasons. And its job is to give some extra filtering when a compressor first starts up. So let's just recap what we've done here. You're not looking at a confusing mess anymore. You can now look at a compressor P&ID and actually read the map. You can trace the suction, discharge, and recycle paths. You can spot the key protective gear. And you even understand the physics that dictates why the pipes are the sizes they are. That's a huge step.
But that brings up one last, really critical question. We know where the instruments are on the map, but how do we get their live readings, the actual pressure, temperature, and flow from the physical hardware out in the field? How does this static map become a living, breathing system? Well, that is exactly what we're going to dive into in our next explainer.